Hello everyone, welcome to the new episode of OpenHW TV. As usual, we pre-recorded some content for a high quality experience for you guys. The video is gonna take around 20 minutes, and then Angelo and I are gonna wait for you at the end of the video for the Q&A session live. Thanks a lot. Hello everyone, welcome to the episode 2 of season 3 of OpenHW TV. I'm Davide from OpenHW Group, and today we are going to talk about CV32E40P for artificial intelligence and machine learning algorithms. First, I will introduce you to the PulP extensions, and then Angelo from University of Bologna will talk about custom extensions from Quantized neural networks. Let's first briefly introduce OpenHW Group. OpenHW Group is a non-for-profit organization driven by its members. We have contributors globally, all around America, Europe, Asia. And what we do is developing open source hardware with permissive license and all the software and tools infrastructure to support it. Our members are actually more than 80 as today. And we have members both from the industry domain, and here you see some of them, and from universities. And also we have partners that help us grow the ecosystem and maintain it. OpenHW Group is divided in working groups. We have technical working groups and marketing working groups. The technical working groups is also divided in task groups to focus more on technical details as cores, verification, software, and hardware. Alongside the working groups that are technical and marketing, we have the regional working groups, and they put focus on regional requirements as sovereignty or projects, and marketing for that specific area. And particularly, we have the European working group and the Asia working group. Now let's jump into the technical side of this talk, and let's start with PulP extensions for machine learning algorithms. So let's give a context first. We are in the Internet of Things, and we are talking about edge computing devices. So we have our chain from data to servers. We have microphones, cameras, and biosignals that are gathered from a microcontroller that sends over the Internet of Things those data to servers that then compute some features and tell us the feedback or the information hidden inside. What we want to do is to be faster and more energy efficient is bringing computational capabilities at the edge. The edge means close to the sensors. And to do that, we have to make the microcontrollers more performant, but still keeping the low power nature of battery powered applications. So how can we do that? At ETH Zurich and University of Bologna, we actually developed the PulP microcontroller. PulP stands for Parallel Ultra Low Power Platform, and the PulP architecture actually combines near threshold computations to achieve high energy efficiency and parallelism to achieve high performance. The compound of the two gives us a wide range of performance and power figures. So from low power single core to higher power but higher performance multi-core applications for more hungry applications like neural networks. And the main core of the PulP architecture is actually the CORE-V CV32E40P. The CV32E40P core has been extended with custom extensions. Those are called PulP. And they are basically a set of extensions that help the core running applications like pattern recognitions faster and also with smaller code size. So we have in several groups of extensions. We have the memory extensions, for example, auto increment, load and store, or misaligned memory accesses that basically help us handling memory operations. For example, In most of the pattern recognition algorithms, you have a loop over a vector. And so that translates to load those elements from memory and then updating the pointers of those. For example, you have a load and then an addition for updating the pointer to the next element. If you fuse those two instructions, you have one of those custom extensions that is the auto increment load that you see on the right. As I mentioned, loop, instead of using branches as the plain RISC-V and the overheads that come with branches like the penalties, the counters and so on, you can use zero overhead. So those are machines that are programmed at the beginning of the loop. They know ahead the end of the loop and the number of iterations. And in this way, you save a lot of overhead. Then you also have bit manipulation, DSP, and packet SIMD extensions. Those are precursor of the RVB and RVP RISC-V extensions. The bit manipulations are those extensions that actually handle packets of n bits. So for example, if you want to count the number of ones in a word, you will need with plain RISC-V a loop of 32 iterations for each bit and checking whether it's one or not. Whereas with our custom extensions, you only have single instructions that counts the number of one in a single cycle. With the DSP packet SIMD, for example, you can handle vectors or packet vectors. So in a 32-bit register, you can fit 4 8-bit elements or 2 16-bit elements, and then processing them with special extensions in parallel. To make an example, here we can see the DotProduct. The DotProduct is a central kernel for all AI applications. And here on your left, you can see a plain RISC-V implementation that needs to load 400 times, in this example, elements from memory, multiplying them, incrementing the pointers, accumulating the multiplied values, and so on for 400 times. Whereas on your right, you can see a loop that iterates only 50 times, and those 50 come from the loop unrolling, so divided by 2, and divided by 4, because instead of loading bytes, we are loading words. So we are loading 4 elements at a time. And then we are multiplying them with a single DotProduct instructions, so from the packets in the extensions, and accumulating them. And like this, we can run our kernel 9 times faster. Another example is the 2D convolution, that is the central kernel of convolutional neural networks that are the main algorithms for image processing, video processing, or any, in general, 2D data. And you can see from this slide that in few instructions, like 7 DotProducts and a few move and shuffled instructions, that you can compute your 5 times convolutional filter is only 20 instructions. That translates in a very efficient implementation of your CNN. Like this, you also put less pressure in memories, thanks to the shuffle instructions, which means also lower power. And running at 670 megahertz in GF22 implementation, that means you can do 2.7 almost billion of max per second. It is a very competitive performance. In the project 2 of the CV32E40P, our main focus at OpenHW will be verifying at industrial level the XPulp extensions. So that means achieving the full code coverage of those extensions, extending the reference model for the step and compare implementation, and also extending the Gcc Compiler to actually support automatically all the custom extensions in your C code. And next to this, we are also want to verify the floating point extensions to have a full complete computer at the edge. So thanks a lot for listening. And now I'll give the ball to Angelo that will continue this with quantized neural network. Thanks a lot.
Thanks, Davide, for the introduction. Hello, everyone. I'm Angelo Garofalo, a PhD student at the University of Bologna. And today I'm talking about the activities carried out at the Unibo and ETH Zurich to enable the end-to-end execution of quantized neural networks on top of the PULP platform. As you may know, there has been an even increasing interest in the last years into the deployment of complex AI algorithms at the extreme edge of the IoT. Many new neural network models have been built from scratch to target the specific requirements of these tiny edge computing platforms. Moreover, it has been demonstrated that coupling these models with aggressive quantization techniques into the integer domain allows to reduce the memory footprint of the network by a significant factor, while without significantly sacrificing the top one accuracy. That's why quantized neural networks are the natural target for what is called tiny machine learning. To enable such workload on top of PULP, we developed an open source software library which leverages an optimized computational model for convolution routines. In this case, basically, the convolution is split into different phases. The first one is the im2call, which basically rearranges a subportion of the input feature map within the receptive field of the current filter into a 1D vector, so that the convolution is transformed into a simpler matrix multiplication kernel between the im2call buffer and the weights to produce the output pixel. The interesting thing is that the same im2call buffer can be reused over multiple weights to increase the throughput of the computation. The matrix multiplication in PalpaN has been highly optimized to exploit the PULP extensions that Davide introduced before. And also, the entire workload has been parallelized over the 8 cores of the PULP cluster. Thanks to these optimizations, we are able to show 1 order of magnitude better energy efficiency on these workloads with respect to the state-of-the-art solutions. But PalpaN is not so efficient when we target sub-byte or mixed precision kernels. The reason is that the CV32E40P processor does not support sub-byte simple arithmetic, meaning that whenever we want to target these kernels, we are required to add extra unpacking instructions that degrade the performance. Well, we tackle this problem, this issue, from another perspective by proposing 2 different solutions. The first one is a set of domain-specific instructions that extend the PULP ISA and deals with sub-byte kernels, coupled with a fused MacLoad instruction that increases the Mac operation efficiency itself. The second solution is the dynamic BitScalable execution core, which deals with mixed precision operations. Both the approaches, both the solutions, do not jeopardize the general purpose nature of the CV32E40P core, meaning that they have low impact on the PPA metrics of the core. XPulpN is built on top of XPulp, and basically it extends the arithmetic simmed operations to nibble and crumb operands. This means that whenever we target sub-byte kernels, we do not need anymore to explicitly unpack the data. And this leads to a significant performance speed up with respect to the CV32E40P original processor. In addition, the MacLoad allows us to improve even more the efficiency because it amortizes the cost of load operations within the innermost group of matrix multiplication kernels. The idea here is to fuse 1 Mac operation with 1 load into a single cycle latency instruction. And the principle is to prefetch the next Mac operand while we are consuming the current Mac operands during the current DotProduct instruction. This basically allows us to improve resources utilization up to 94%, bringing to an overall efficiency, energy efficiency boost of 1.5 times compared to a classic execution with load and DotProduct instructions. But still, this is not enough to target mixed precision kernels because we would pay anyway a little overhead to bring the lowest precision operand to the same precision of the highest precision operand. To solve this issue, we basically extended the data path of the processor to handle all these type of instructions directly in hardware within the sum of the product instruction. And as you can see here, we save a quite significant factor in terms of instructions. But the problem now moves at the decoding stage, because if you want to encode one instruction for each format and type of SIMD operation we want to perform, including mixed precision instructions, we end up adding an enormous number of instructions. We increase a lot the complexity of the decoding stage and also the ISA encoding space. That's why we followed a different approach, which we call dynamic bit scalable execution. In this case, the decoder issues only the virtual SIM instruction that encodes only the type of operation to be performed, while the format is specified at runtime by the content of a control status register. As you can see here, the pressure on the decoding stage is reduced by a significant factor. Moreover, this approach allows us to reuse the code, meaning that we can write format agnostic routines that can be specialized at runtime by writing the control status register. And in this case, basically, we are able to improve the performance of the CV32 processor also on mixed precision kernels. Now, if we compare our hardware solutions with respect to the state of the art in terms of energy efficiency, we see an improvement of up to 3 orders of magnitude. And this improvement is given by the ISA extensions coupled with an optimized library, thanks to the cluster parallelism, and thanks to the implementation of PULP in leading-edge GF22 technology node, a much more scaled node with respect to commercially available STM32N nodes. Now, the interesting part is that what I presented so far is not meant to be standalone, but it is meant to be integrated into a vertical flow that we developed at Unibo to handle end-to-end deployment of quantized neural networks on top of PULP. So basically, starting from the specification dataset, full precision floating point model, we have the first tool, NEMO, which handles the training, the quantization, to generate a full integer representation of the network. This network feeds the second tool, which is Dory, and manages all the data transfers among the memory hierarchy of PULP in an efficient way. And it incorporates PalpaN as backend computing library. The output of Dory is a compiled C code, is a binary that runs on the underlying platform. The underlying platform that exploits the low bitrate integer arithmetic support that XPalpaN guarantees. Now, in this talk, I covered only these 2 pieces of the flow, but all our code is or is going to be open source, and also you can check out papers, technical reports on all the topics basically covered in this slide. And now the most interesting part is that this tool really enables real-world AI-enhanced IoT applications. So the first demonstration is the end-to-end deployment of a Mobilenet V1 model. As here we can appreciate how efficient it is, the Dory tool, and which basically brings the overall performance of the Mobilenet to outperform the state-of-the-art solutions by up to one order of magnitude. And then another important and nice applications concerns the full autonomous non-drones navigation. We were able to train and deploy a full DroneNet on a PULP shield, on a PULP embodiment, which powers a little drone. And as you can see here, you can check the papers, the code of the implementation, but also you can appreciate some live demos that we uploaded on the PULP platform YouTube channel. Apart from this, many other projects are still ongoing that exploit the vertical flow developed at Unipo. In the last slide, I am putting just some references that cover all the topics presented before. So thank you for listening, and thank you for your attention.
Thanks a lot, everyone, for listening to this presentation, and thanks a lot, Angelo, for for actually your presentation on quantized neural networks. I think there are quite a lot of people connect. If you have questions, please type them in the chat. So far, we received offline some questions. Maybe start from them. Meanwhile, please write your question live. So the first one is about the compiler. Maybe I start and answering, and then Angelo can complete the answer for the side. So the question is there any compiler support for the PULP extensions and in general for the PalpaN as well extensions, and how can we use all these instructions in our C code? So most of the PULP extensions are actually implemented in a GCC supported version from the PULP group maintained by, as today, ETH and the University of Bologna. So there is a GCC compiler in the PULP platform GitHub that is, I don't know which version it is, I think 7 or 9, I don't recall. Angelo, if you know better, please say that. But and this compiler will translate your C code to a binary that contains most of the PULP extensions, except some of them that are hard to be, let's say, automatically inferred from the C code, as, for example, the DotProduct. So for the DotProduct, the current version needs the programmer to explicitly call a built-in function that is called built-in _ DotProduct, something like this. You see all the examples on the open source applications that Angelo mentioned. That actually translates to the DotProduct instructions that we have been talking about in the meeting. But OpenHW Group comes together with the University of Bologna are actually implementing the PULP extensions in a fork of the GCC compiler that eventually will be streamed up in the main RISC-V GCC repository, maintained by the whole community, not only OpenHW or Unibo and ETH. And here we are also moving all the decoding of the instructions in a custom space, so doing everything, let's say, at the industrial grade with a test of the compilers, test of the instructions, and a new encoding space. Maybe Angelo, do you want to comment about the specific PalpaN compiler support?
Yeah, sure. And yeah, basically what I can add is the compiler support for the XPalpaN extensions, for example, is not so trivial because, as you might know, the lowest data precision that you can play with into the compiler is the byte. So basically, it's hard to handle nibble or crumb operations. Despite this, we have some kind of support on the compiler side through the built-ins, as Davide said just 30 seconds ago, and which offers, let's say, a higher grade of freedom than just inferring the assembly code. Because with the built-ins, together with the built-ins, we extended also the backend of the compiler. Not the front end, of course, but the backend, we extended it to support the nibble and crumb operands. And in this way, basically, you allow the compiler to do some basic but important optimization steps, like, for example, solving some data dependency if possible, or build a more structured code. But what I can say more for the PalpaN plus XPalpaN framework, let's say, is that this is not a concern at all. I mean, the not fully supported instructions into the compiler has not been so far a concern from our point of view. And the reason is that PalpaN is not meant to be exposed to the programmer, let's say, to the average C programmer. And this is possible because there is a middle layer, which is Dory. So basically, PalpaN is the backend of a more flexible tool, which is Dory, and handles, apart than the computing kernels, also the explicit data movements in a very efficient way. So yeah, as I said, this is not a real concern on our side for QNN applications, let's say.
Since you mentioned Dory, I answer a question. I repeat a question. I report here a question that actually regards Dory. Are all the kernels supported in Dory, or do you want to comment some more specific details of Dory on the kernel supported formats and filter size and all these parameters of neural networks?
Okay, yeah, I got the question. We are currently working on extending the Dory tool with the support of more and more PalpaN based kernels. And for example, at the moment, Dory does not support the mixed precision kernels executed in this status-based way, what we call a dynamic BitScalable execution, because in that case, the programming model slightly changes, meaning that in that case, you have one instruction of overhead whenever you want to change the format of the SIMD operation. But the interesting part is that you have only one convolution routine instead of having convolution for 8-bit, convolution for 4-bit, and so on. And this is because basically you can specify the format at runtime. So this type of programming model is not yet supported in Dory, but we are working on it. And this is because basically the status-based execution core is our latest work in time. So basically, we are working on extending Dory also to target this type of execution. As far as concerned the PalpaN plus XPalpaN in a classic way, let's say with the MacLoad and Nibble and Cram support, we have fully support also in Dory for this type of kernels and computation.
Okay. Thank you, Angelo. Another question that came here live, thanks for the many questions, by the way. Are energy efficient numbers based on silicon measurements or simulation? If simulation, what tools were used? Maybe I can answer as you just talked. We can answer both. So we have actually both results. We at the time I was doing the PhD at ATH, and as today also Angelo is doing at Unibo, we've been doing quite a lot of silicon chips based on PULP across several technology nodes, from 130 nanometers, the first version, all the way up to 22 nanometers for sure, and maybe as today even on even more scaled technology nodes. There are many papers about all the silicon measurements, and you can find them on the PulP platform website. So you go there and you see papers. There should be a section at the reference to them all. But we also have done some exploration where we actually didn't produce silicon, and we stopped at post layout power estimation. So doing the whole RTL to GDS flow, but power measurement done with the commercial EDA tools after the backend was completed. I hope I answered the question. Angelo, do you want to say something more?
No, I mean, you basically covered everything. What I can add is that the slide that I presented, the one with the energy efficiency measurements, those measurements are taken from post layout, back annotated, parasitic annotated simulations. And I guess the question mentioned also the tools that we used. So basically, we run the simulations in QuestaSim, and we did a place and route in with the cadence flow. So the most common commercial tools to do backend, and yeah.
We also have done, I think, with other chips were done with the IC compilers from Synopsys, power estimation also with the Synopsys and Cadence. So we use commercial ADA tools. So there's a question that actually fits in exactly in this conversation, because it asks for project source code including multi-core CV32E40P running on FPGA. So actually, I forgot to mention there are also FPGA implementation of the PulP microcontroller, both in single core, and actually the single core one is maintained as today both in the PulPissimo version of ATH and in the Core-V MCU version of OpenHW. So there is a downloadable bit stream, and there's also a multi-core version with this core that is called Hero. That is actually the cluster as an accelerator of an application class core that runs on an FPGA. I think there are also other FPGA implementations today, probably not the most updated for the multi-core, but for sure the ones I mentioned are up-to-date. Angelo, do you know more of them?
No, unfortunately, I don't. I mean, I missed part of the. If you can repeat the last part of your sentence, because I had some internet connection problems. So
no, I just said we have several FPGA implementations for CV32E40P, both single core, and they will be PulPissimo and Core-V MCU. PulPissimo under the PulP platform, ATH and Unibo GitHub page, and Core-V MCU under OpenHW. They are slightly different, but they have the same root, and also multi-core, and that is called Hero, still under the PulP platform page.
Yes, but I guess also the PulP platform. I mean the PulP, so PulPissimo plus the cluster, has the CV32E40P cores also in the cluster. So we
also
have
an FPGA.
Yes, yeah, we have the FPGA flow.
Okay. Another question for you, Angelo. Do you have insights about the MacLoad, like at architectural level?
Yes. Okay. So if I understood the question, I should go a bit more in depth in the description of the MacLoad. I mean, so basically, it's hard to answer without a schematic or something, a diagram, but I can try. Basically, what we wanted to do with the MacLoad is try to fuse the DotProduct operation with the load. And the reason is that most of the cycles, I mean, not most of the cycles, but a huge, the load operations have a huge impact on the performance of a matrix multiplication kernel, because of course, in a classic approach, you need to bring the operands from the memory to the register files. So at least you pay to load instructions. And so it's, of course, really beneficial to hide or to reduce the cost of this type of operations into the kernel. I mean, you would like to have basically only DotProduct operations. And one way to do that is trying to prefetch the operand that you are going to use, let's say at the MacLoad 2, when you are executing at Mac operation 2, when you are executing the Mac operation 1. And to do that, basically, we exploited the data reuse that is possible on convolution kernels, especially in the matrix multiplication implementation, And so our idea is, okay, in the current cycle, we have part of the data path that is used to do the dot product operation, but we can basically reuse another part of the data path to issues a request towards the memory, in order that at the next cycle we already have in a dedicated register file, and this implementation was chosen basically to amortize the area and power costs. So basically, this small register file contains the operands prefetched, and that can be reused over the next Mac operations. And this is a lightweight method to basically amortize the cost of loading operands into the matrix multiplication without having a huge impact on the power consumption of the core. And so this lightweight method, as I showed in one of my slides, is really giving a significant boost in terms of energy efficiency. And also, thanks to this, basically at every cycle into the matrix multiplication kernel, you are doing real computation. So the utilization, the hardware utilization, as you have seen before, is close to 1, which is 200%, which is, let's say, the upper limit for the single issue in order, single instruction issue core. Yeah.
Thank you. Related to this, that's another question that says, have you already implemented the fused DotProduct for XPulp RISC-V? And then yes, Angelo actually implemented, but it's not under XPulp extensions, but it's XPulp NN, which is an extension of the XPulp extension. So extensions of an extension that target specifically neural network, and they are also open source, but as today maintained by University of Bologna. And can you share some links to the XPulp papers and code? And yes, again, it's under the PulP platform webpage. I can let me just copy the link in the chat such that everyone has the reference to where you can find all the papers of ATH Unipo regarding PulP. And still the same person asked, where can I find the slides and link to this presentation? Everything is going to be uploaded on the OpenHW Group TV channel of YouTube. So if you go on YouTube and type OpenHW Group TV, see the channel, you see this episode and all the previous ones. Okay. Okay, we still have a couple of questions. Maybe one for Angelo and me together. It doesn't specify of which extensions we're talking about, but it's how do you deal with the overflow for the PulP extensions? So I can say in the PulP XPulp, and then maybe Angelo can enrich the answer with PalpaN. So we actually follow the RISC-V philosophy, and if you are familiar with RISC-V, there's no explicit handling of the overflow in integer instructions. So if you have two integers adding up together or multiplying, and they overflow, there's no overflow flag with other kind of machines, and there's no overflow exceptions, and there's nothing like this. So you need to handle in software. We actually follow the same strategy. We offloaded to software the deal with overflows. And Angelo?
Yeah, basically we followed being the extension of the extension, we followed the same approach. So yeah, I have nothing to add on this aspect, but maybe I don't know if the question was because, you know, many times I was asked to discuss about rather than the overflow, about the leftover in the matrix multiplication kernels, for example. So how you handle the leftovers while you use a SIMD approach, because this is I mean, maybe the question was related also to this. And the reason is basically that if you have leftovers, you lose a little bit the performance and the energy efficiency, because, for example, the data does not is not the number of data you have to process is not anymore a power of 2. So in that case, you might choose different solutions to handle this. And for example, if you think about the first layers of a CNN, mostly for image classification. So the very first layer is has 3 channels, the classic RGB channels. And in this case, one trick to not lose at all efficiency is to do some padding, some artificial padding, in order to have in the end a 4-channel image, but with a 4-channel which is basically fake. And this we experimented that it is faster than handling the kernels without the SIMD approach, because otherwise the other solution is that I mean, if you have 3 operands to process, you cannot pack them into a 32-bit register, because you have one last piece which is not covered. So instead of using scalar operations, one possible solution is to do this padding, this fake channel. And we have seen that basically this allows us to more or less keep the same energy efficiency as the other layers.
Thank you, Angelo. I think we have the last question. Do you have any plans to submit proposals for official extensions with these new instructions, or will they likely remain PULP only? These are very good questions, actually. Thanks a lot. So the PULP extensions actually were born 2015. I think it was 2015, and it was even before the proposal, for example, RVP, where they overlap quite a lot from RISC-V in terms of packet SIMD and DSP instructions, and RBB, so the bit manipulations. So that are also part of the PULP extension. So they happened before, and of course, as we always have been publishing the RTL and the spec open source, they and participating to all the RISC-V summits and conferences and meetings. We, of course, influenced a bit both the RVP and RVP extension. So the current RVP and RVP are somehow already kind of including part of the PULP extensions that contains even more things. And but of course, once you switch to the RISC-V ecosystem and not only the custom, you have to fill many more requirements that goes from low end to high end application processors, different kind of rules. How do you fit in the encoding space? Which encoding space are you taking, and etc. Another extension that we didn't mention here is that even before the shared register file, which is now called ZFNX, shared floating point register file, was proposed, we had actually already made a silicon implementation with the shared register file and the custom compiler. And once we published those numbers, also in the RISC-V community, the ZFNX was proposed to actually share the register file between the floating point and the integer. So we are already active. We are quite active in the RISC-V community. We've been always publishing. Of course, they will never be one-to-one. So custom extension will never become exactly the proposed solution as they are. I hope I answered the question. And I think we don't have more questions in the chat. So at this point, I would like to thank you Angelo, for your presentation, and thanks everyone for listening. And I hope you enjoy the video and the contents, and feel free to send us email or comment the YouTube, send video once up, and we will be gladly replying you. So bye everyone.
Thank you. Bye.